Hello, this is Dr. Lewis, just going over some material from my course on structure and reactivity that will be covered in the exam assessment. This section on organic reaction mechanisms was part of a lecture that you were unable to attend because of the lockdown. So the lecture was written basically after you left, and then I uploaded it as a panopto recording from home. So please look at the lecture material called L4 Organic Reaction Mechanisms. So we looked at one sort of reaction, organic chemistry reaction, the substitution reaction. Is where you swap one group for another. So in this case we swapped ethoxide OCH2CH3 for Cl. So now instead of Cl we've got OT and we've got chloride displaced. And there's two possible mechanisms that can occur. One is called Sn2 and one is called Sn1. Obviously you have to read the notes to get a detailed explanation for that. Sn2, which is actually the one that occurs for this particular reaction, the label stands for S substitution, N nucleophilic, and 2 second order kinetics. So second order kinetics you'll have done in Dr. Horozov's course. It also corresponds to bimolecular. So to identify whether it's Sn2 or Sn1, first look at the substrate, the organic substrate, which is the electrophile. And there are basically two things reacting with each other. The nucleophile, and we'll write sodium ethoxide like this. That's the electron donor. And then the electron acceptor. And this is where it's going to accept the electrons, because this carbon is polarized delta plus, delta minus. So it's going to, the electron donor is going to attack the electron acceptor, which we call the electrophile. And the most important thing for identifying with Sn2 or Sn1 is the reaction center. Is it primary, or in this and the other extreme case we looked at was tertiary? That's primary. And when it's primary, it will undergo Sn2. Because bimolecular means that the two groups, the nucleophile, come together with the electrophile in a single transition state. Bond breaking and bond making happen simultaneously, and therefore at some point we have 5 groups attached to that carbon. The nucleophile as well as the leaving group. So we have a sterically, potentially crowded carbon. So if you have a tertiary carbon where you've got R groups here, alkyl group, that's too crowded to undergo this mechanism. But it can undergo this Sn2 mechanism where the nucleophile comes in and then at the same time it forms a bond at the same time as a bond between C and Cl break. So that's the key thing. Look at the substrate. Is it primary or is it tertiary? Now we're not going to do secondary because that's always a trickier one to do. So we'll just look at primary and tertiary. So as for a curly arrow mechanism. So a curly arrow mechanism doesn't involve drawing the transition state. It involves showing where the electrons start and where they finish. So that's our substrate, which is polarized like that. And that is our nucleophile. It's going to donate its electrons to the electrophile. It's got a negative charge. So one of those lone pairs starts there. So your curly arrow starts with a pair of electrons. It finishes where the bond's formed, and then at the same time that bond breaks. So now we've formed a bond from that oxygen to that carbon. So we can draw what the curly arrows tell us, which is this is our product. O, and now that's attached to that other part of the oxygen. So we've got two lone pairs, and because we've broken that bond, we've now formed chloride as a leaving group. We've also got our sodium and our sodium, but that's all we're going to say about sodium. We're not going to involve it in any colors at all. So what is the rate equation? So the rate, say it's a bimolecular process, so it's going to involve two things, both the nucleophile and the electrophile. So rate is going to be K times the nucleophile, and we'll just call the electrophile RCH2Cl. So it's second order to the power 1 to the power 1 adds up to be to the power 2. What about what favours Sn2? Sn2 favoured by a primary carbon at the electrophilic reaction center, we'll call it. Well, various things that favour Sn2, and I've listed them in this summary. Polar aprotic solvents. We haven't got a solvent listed, so that's not relevant. The leaving group, chloride, is not a particularly brilliant leaving group, so it's not particularly weak bond, that. But in this particular case, we've got a strong nucleophile. So ethoxide is a strong nucleophile. And that's mainly due to the negative charge on the oxygen. So if it was a neutral version of that, ethanol, it would be a relatively weak nucleophile. So by removing a proton, making it ethoxide, we've converted it into a strong nucleophile. So they're the two things, but the most important thing is it's a primary carbon.